Hey, what's going on, everyone? So, about a week ago, I spoke at DEF CON 34 for the mobile hacking community, and I did a presentation on leveraging Frida to bypass mobile application security controls. And I wanted to run through the presentation and upload the video to my YouTube channel just for those who want to see the contents of this talk. So, the agenda for this presentation is we're going to review a target application that I built that's meant to emulate a recent pen test. We're going to talk about Frida and then use Frida to enumerate an iOS application security controls. Talk about mangling, look at Frida CodeShare, and then finally bypassing those security controls and then some references to wrap things up. So let's take a look at this application. So I created this iOS app and it's meant to, again, replicate and emulate a recent pen test that I did, where if I tried to run the application on a jailbroken device, we would be presented with security check failed. We have detected your device to be jailbroken, which is not compatible with our app, and then the application would immediately close. So I am using Pale Rain for the jailbroken iPad, and the package manager is Silo, and this is to show you right off the bat that I have something called Frida server installed on the iPad. So as you can see right here, Frida 17.16.4 is installed on this jailbroken iPad. So what is Frida? So Frida is an open source dynamic instrumentation toolkit that enables developers, reverse engineers, and security researchers to inspect, intercept, modify the behavior of a running application in real time by injecting JavaScript-based hooks into native or managed processes. Frida provides deep visibility into function calls, memory, APIs, and system interactions without having to modify the application source code or rebuilding the target binary. And then Frida follows a client-server architecture. So on the developer machine, this would be my Kali box. I have JavaScript instrumentation code that I wrote that defines which functions to observe or modify. This script is sent to the Frida server, which is located on the jailbroken iPad. Again, that was in one of the previous slides, just to show you from there, and which attaches to or spawns the target process and injects the Frida agent into it. The injected agent then executes the JavaScript within the context of the target process. Once loaded, the agent enables hooks that intercept function calls and observes or modifies the application behavior at runtime without changing the application's binary on disk. So we have on the left-hand side, this would be my Kali box where the JavaScript code is stored. And then we have the target device, which would be the jailbroken iPad. And then that's where the Frida server was installed. So the Frida TAC PS, TAC UA is going to be a sanity check just to make sure everything is running properly. So on my Kali box, I have Frida running, and over USB, it's able to talk to the jailbroken iPad, and the TAC U is for USB, and then IA is to show the installed applications. And as you can see here, we have one called com.darkbank.defcon, and that's going to be our target for this presentation. So let's dive into our first script. So we have the command up here that we run that's going to leverage this script. And quickly put, this is Frida TAC U for USB. TAC L is going to be to load the script. So we're going to load listclasses.js and then spawn the process com.darkbank.defcon. And looking at the code, this is going to see if Objective-C is available. So is the runtime present? If not, we're going to display to the terminal, Objective-C is not available. But if it's successful, it's going to say successfully connected, detected Objective-C, and then we have a simple for loop in here. So this is going to loop through the Objective-C classes in that spawn process, take those classes, store them in class name, and then we're going to output that to the console using console.log and then that class name. So let's go ahead and run listclasses.js and see what it does. So it's booted up, it started, and we can see all of this output right here on the left-hand side. And then once it's done, we'll see the little pop-up right here, and we see just tons of classes being outputted from this process. At this point during the engagement, I wanted to narrow my search a little bit. So I used regular expression to observe something that I thought would be very easy or obvious to point out. In this case, so jailbroken right here. So the next script is going to show that I just modified the previous script and I add this variable in here, regex, and this is going to look for anything that starts with JLB and then ignores the case. So this could be capital J, lowercase j, it doesn't matter. And then we have this if clause in here, so if the class name matches the variable in the regex, just output that. So now if we run this, list classes filter.js, we see iOS security suite.jailbreak checker. So we greatly reduced it down to just one thing to kind of enumerate and go through. So doing a Google search of iOS security suite, we find a GitHub repository. So this is open source, and this is a security suite that's Swift based, and it provides jailbreak detection, debugger detection, and anti-tampering related checks, and it's again purely written in Swift. So that is what we're up against. So the next course of action that I took was just trying to see if there's any useful methods. So I modified the script again, and instead of just looking for the classes, I'm going to now specify this class name variable and look for iOS security suite.jailbreak checker, which is what we learned from the last script. That's going to be processed in here, so the Objective-C classes, and then specify iOS security suite.jailbreak checker. And then we want to enumerate those methods, so we have a for each loop right here, so the CLS methods, and then for each, and then console log, so display to the terminal, everything that you find regarding that. So now if we run listmethods.js, we see some output here. Now, during the engagement, I processed and read through this, and to kind of keep the conversation short, I did not see anything worth value from this. While there's certainly information in here, nothing screams to me jailbroken or something that would be something worthwhile trying to bypass. And again, what I referenced in one of the previous slides was this security suite is built purely in Swift. So this is a pivot from Objective-C to Swift. So Objective-C classes expose methods through the Objective-C runtime, allowing Frida to enumerate them with Objective-C classes and methods. Pure Swift methods are generally not registered with the Objective-C runtime unless explicitly exposed, so they cannot be discovered through the Objective-C classes. Instead, we're going to enumerate Swift symbols and use Swift mangled symbol names, which is quite a mouthful, to locate native functions for analysis and instrumentation. So we're going to go from looking at Objective-C to now Swift. So we have the command up here, and now we have this JavaScript script that's going to now check if Swift is available and do this sanity check again and display if Swift is available or not. And then if so, we're going to create this module map object right here and then loop through the values of that module map. And we want to return any of these symbol names that include iOS Security Suite, and we're filtering those out and storing that in the matches variable. If the matches length is greater than 0, so we hit this if statement, we're going to say console logged found and then the matches length. And then what we want to do then is iterate through those symbols and abstract the symbol address, so the memory address, and then the symbol name. And what that's going to look like is this. So it's finished running, and I'm going to scroll up just a little bit. Pause here, and let's review this. So we see the $S16 iOS Security Suite, AAC 10, MI proxied, MI debugged, MI jailbroken. I don't know if you can see my mouse cursor, but there's all of these various different symbols in here from that output that it's a little human readable, but not fully. And I can kind of tell you a little bit. So the $S, that stands for Swift. The 16, I believe, represents the character count. And then AAC, I believe that's for class. 13 again is the character count, and then the capital S, B, Y, capital F, Z should determine that's a Swift Boolean of static type and that's a function. So here's the problem. I'm not going to memorize that or understand it fully. So what I went ahead and did is I used a utility called Swift demangle. So in compiler construction, name mangling is a technique used to solve various problems caused by the need to resolve unique names for programming entities in many modern programming languages. Swift uses name mangling to encode information such as types, namespaces, function signatures into symbol names used by the compiler in runtime. The mangling format can vary between Swift versions. When reverse engineering Swift applications, so what we're currently doing, these mangled symbols are commonly encountered in disassembly and symbol tables. The Swift demangle utility converts them back into a human-readable form, making it easier to identify functions for analysis and Frida hooking. So let's take an example, the mi jailbroken one that we saw. So we're going to echo this string, pipe that into Swift demangle, and then this is the output that we would get from this. So we can observe that this is static, iOS security suite, mi jailbroken function, and this returns a Boolean. And that, to me, that makes sense. So in my head, I'm thinking, well, this is returning a Boolean, so it's checking the iPad. This function's being called. Is it jailbroken? It is probably returning true, so that is the Boolean value. So that's the thing that we want to start looking for. So let's actually take, though, all that output and do a little bit more enumeration. So I'm going to run that Swift symbols.js file again, and I'm going to store that in output.txt here. So this is going to go ahead, boot up the app, run, and it's going to store everything inside of output.txt, which then we can cat that file out and pipe that into Swift demangle. So everything should be stored in output.txt, and the next slide is going to be us catting that out, piping that into Swift demangle, and then we can observe everything that's inside of that file. And yeah, so static iOS security suite, mi jailbroken, Swift Boolean, deny debug, mi run in emulator, mi in lockdown mode, mi proxied, mi debugged, so on and so forth. We see all of these mi, etc., and they're returning some Boolean value. So this is the part where I've enumerated it. I figured out like kind of what the issue is. I'm going to now go and look at a site called Frida CodeShare and do a search there for iOS Security Suite. If you're not familiar with Frida CodeShare, it's a public-facing website that has repositories for Frida code. I use it quite often to not only find proof of concepts like this that would help me potentially bypass these security controls, but also as a learning tool. This is just a library of Frida scripts that you can pull down, reverse engineer, and what I like to do is find these code like these code snippets, open up documentation and read through it and understand this Frida API and everything that's happening within here, so I better understand how to program my own Frida script. So that's just my little takeaway from this. But for the purpose of our presentation, what we want to do is use something like this Frida code snippet here, this repository, to bypass those security controls. So this one checked all the boxes for me, and there's a command in here where you can actually just take this script and run it directly onto the iPad or whatever device you're targeting. My rule of thumb is I like to review the code, read through it, and just make sure I understand what it's doing and make sure it's not doing something nefarious before I run that. And that should be a rule of thumb for you for anything that you find on GitHub, the World Wide Web, whatever. Read the code before you run it on any sort of target. But anyway, so I pulled down that code and I put it in CodeShare bypass.js. The main thing that we want to look at is this function in here. So inside hook iOS security suite, there's going to be a variable called mod, and this is going to store process that find module by name iOS security suite. If it's successful, we have this try block in here, and we're going to take that mod, enumerate the symbols, and then again, we're looping through those, and we're looking for ones that end with the S, B, Y, F, Z. And then the main thing to point out here is this on leave event call. So I did add these two comments in here just to be very transparent and clear about what this script is doing, or at least this function. This is going to set the return register x0, so this, to 0 using this native pointer function. And that's pretty much saying any of these symbol names that you discover end with the SBYFC, so am I proxied, am I jailbroken, am I on a debugger, etc. Find those and set the return register to 0 and force them to return false. So that's what this script is doing. So now let's run this and see what happens. We're unfortunately still getting that security check failed message. So oftentimes what I'll encounter or see from other individuals, either through maybe capture the flag, on a penetration test, whatever the case may be, you find a snippet of code and it checks off all the boxes. Let's say it does 95% of the work. If it didn't do 100%, they take the code, throw it in the trash, and they just keep repeating the process. So we could just go to Frida CodeShare and just keep copying, pasting snippets of code till we find one that works. But I want to show you something and maybe shed some light on something that maybe in the future might help you. So let's review static linking versus dynamic linking. So dynamic linking, the example on the left-hand side, the library remains a separate Mako image loaded at runtime. Okay. Static linking is the library code is linked into the application's executable at build time. So that's what potentially we're dealing with. A statically linked library is merged into the application's executable instead of being loaded as a separate Mako image. Therefore, Frida must enumerate symbols from the application's main executable rather than a separate framework. So let's hop back over and look at this. This is saying process that find module by name, iOS security suite. So it looks like it's leveraging dynamic linking in that script. And I have the process that find module by name and then the get module by name. And these return a module whose address or name matches the one specified. In the event no such module can be found, the find prefixed, which is this one, returns null, and the get prefixed one throws an exception. So going back to this, we have the find module by name, and I included both of these just for completeness sakes because if you review the Frida documentation, they're side by side, so I just felt I needed to include them both together. So what's going on is it looks like this is returning null because it's trying to find module by name, iOS security suite. That's returning null, so we return false here. And we're not able to actually execute anything else that's in that try block, for example. So what if we just made a simple change to that script? Instead of the process that find module by name being iOS security suite, we targeted our application and assumed that the iOS security suite is bundled within the application and statically linked. So here's the last script that I wrote, and the main line of code is this one right here. Console.log module name is, and then we have the process.module main module.name. So let's run this script. So this is going to get name, and then the module name is darkbank. It should be no shock, but now we know the proper name for the application that we're targeting. And now let's just simply update the process.find module by name to darkbank, knowing that that's particularly where all of those function calls are being made. And now hopefully all of this will actually execute. So let's run this script after making our slight edit and see what happens. And as you can see, we have more output on the terminal, and it looks like the application is now usable on the jailbroken device. So we can log in and have full access to the application, and we have bypassed those security controls. And we can see it hooked into the am I jailbroken, am I run in emulator, am I debugged, is parent proxied, all of these, right? So these are all listed in here, and we bypassed them and forced them to return false in memory. So the key takeaways. Frida enables runtime analysis without modifying or rebuilding the target application. Application enumeration is the foundation of successful runtime analysis and identifying Objective-C classes, Swift symbols, and implemented security controls before attempting a bypass. Swift name mangling can obscure security-related functions but tools such as Swifty Mangle makes those symbols more human readable and understandable. Frida hooks code loaded into the process with static linking. Library code becomes more part of the application's executable rather than a separate framework image. Understanding how an application's security controls are implemented is often more valuable than relying on generic bypass scripts. So that kind of takeaway is don't just go to something like Frida CodeShare or GitHub, grab scripts and throw them at your target just to kind of see what sticks. So this is fully enumerating and understanding the application because it just might be one little line of code or one little change you have to make to get everything working. So finally, some references. If you're new to Frida, I would recommend reviewing the top two sites, frida.re, its main site, and then Frida Basics to learn the basics of what Frida is doing. Here's Swifty Mangle, which is what we used earlier in this presentation. iOS Security Suite, here's the security controls that we bypassed. Here's the Frida CodeShare that we used. And then this blog helped facilitate a lot of the contents in this presentation, so I wanted to give it a reference. And last but not least is this OWASP Mobile Application Security Testing Guide. There's a lot of good information in here, so whether you're a seasoned vet or just starting off in mobile application security, this is something I would recommend reviewing, as it'll walk you through methodology, documentation, tooling, etc. to help you get started. So that pretty much wraps up this presentation. I hope that you found the contents of this video valuable. If you have any questions, please feel free to leave a comment below. You can also reach me on my website, owlhacku.com, Twitter, LinkedIn, etc. I look forward to hearing with you and to answer any questions that you might have. So other than that, I have nothing else. Have a wonderful day. Thank you for watching my content. Happy hacking and take care. Thank you.